Hi and welcome everybody here. After the two presentations, now it's my turn. So I will talk about um, uh, IEEE 1547 compliance and practical implications. We will talk about DERs, voltage right through requirements, and various other topics. So I will just mention these topics I will be talking about. So right now on your Windows, you have two presentations. One is the presentation that you see, the large one. Then another is the file here at this side. This was actually given to us from the instructor, and we have to give the reference and talk about it accordingly. And then on the top, I'm just trying to show you some video related to smart grid, but you have to put your concentration more on this black slide. So starting from here, let's begin. We will be talking about voltage right through requirements, category 1, then the category 2 and category 3, and we'll talk about journal notes on voltage right through and VRR requirements, and we'll talk about a low voltage right through LVRT requirements, high voltage right through, and then we'll talk about frequency right through, and we'll talk about the general requirements for FRT, and then the rate of change of frequency right through. We will also talk at the end about frequency Droop capability, and the last section interoperability of DRs, and then after this Mohammed will continue and he will conclude. So let's begin and talk about our presentation, and meanwhile I will be also moving the actual slides, the actual presentation that was given to us. So for in this case, we're going to talk about we'll define distributed energy resources. Just 2 3 minutes I'll take importance of voltage right through, and just an overview of this. So DERs are similar power generation or storage resources located closer to the consumers. Say like we say the solar panel, wind turbines, battery storage. So we all know it's not a new thing for us. Then bulk power supply BPS is actually this is about the high voltage transmission network that carries electricity over a longer distance. Then reliability, we talk the ability of the BPS to deliver electricity consistently. And the topic of today is disturbance right through. So there's various kinds of disturbances in terms of voltage and frequency. So we'll talk about those in detail. So the category 1 is DER. We'll talk about the minimal requirements. Which are the minimal requirements? Uh, One is it is defined by minimal BPS reliability that needs. This means DERs in this category are designed to these that I just mentioned. And one is they should be staying connected during minor grid disturbances, and generally meet basic interconnection requirements. This is very important, and they should be able to achieve with most common DR technologies. I mean, we should not have to have a very technical or difficult technologies to have it. So, however, a critical point is that category 1 that we are just talking about, that performance is not equivalent to the stringent standard applied to the traditional. We will see after this about category 2 and 3. So and the difference between those. Then what is the problem actually? The core issue is that with the high penetration of category 1 DER, the BPS can become vulnerable, because if you will have a high penetration, all of the sudden the BPS can become vulnerable. Now the issue is that there is a lack of robust right through. Let me continue with the number 2 as well, because we're going to talk about this. And right now you can see a graph here. It looks so small because it's there in the presentation that was given to us. So with this screen, I'm just showing it as a reference right here on your left, under my picture. You can see it. So we can define this as well. Let me just see my video is working. Okay. So we will talk about, we'll continue with the presentation, the lack of robust ride through during grid disturbances like the voltage dips, as we will talk, or the frequency fluctuations. Category 1 DRs might disconnect. There is a possibility. So this sudden loss of generation can exacerbate the disturbance, potentially leading to cascading the failures and the blackouts. So there is a possibility that is the lack of robust ride through. Then the another is the inconsistency with BPS standards, because traditional power plants are required to remain connected and support the grid during disturbances. So the category 1 DER do not actually meet these same standards. So this is like what is happening, as this is creating a mismatch in the reliability capabilities because of this inconsistencies with BPS standards. So now the another thing is the regional impact. The impact of DER penetration is measured on a regional or BPS wide basis because it depends upon wherever those DERs are, and it depends upon the region where they are located. So a high concentration of category 1 in a specific region can destabilize the entire grid. So it is like one of the issue that we can face with category 1. So, what about category 1? We defined category 1 VRT, DR response. We'll talk about abnormal voltages. We'll talk about voltage trip and ride through conditions. And there is a diagram in the presentation that was given to us for category 1 that we can see here. So, I will talk according to this. So in this case, let's move on to we will be talking about category 1 VRT. Minimal requirement is category 1 VRT represents the most basic level of voltage disturbances handling of DLs, which is like very minimum or in the beginning. It signifies that these DRs are designed to withstand relatively minor voltage deviations, not for the huge deviations. So the focus is on preventing nuisance tripping during common small scale voltage fluctuations, not for a larger scale. So we can talk about a limited robustness. Of course, it's a limited robustness. Category 1 VRT does not equate to the robust ride-through capabilities demanded of a traditional large-scale power plant. So this is like for, as I said, for the smaller outages. So let's move on to the next one. DER response to abnormal voltages. So the basic stability we'll talk about DER in category 1 are expected to maintain connections during brief shallow voltage dips or the rises. When the voltage dip is shallow, or voltage dip is shallow, or the rise is shallow, then the DER in this category, they are expected to maintain connection. So their control systems are designed to detect and respond to these deviations. They are designed, or they are manufactured in such a way that their control systems are designed to detect and respond to these smaller deviations, as I said, but with limited capacity for sustained operation in abnormal condition, because it means this is something very limited that we just spoke before. So the potential disconnection we'll talk about when voltage deviations exceed predefined thresholds in depth and in duration, category 1 DRs are designed to disconnect. So this disconnection is a protective measure to prevent damages to the DRs and to avoid the grid disturbances. So this is like potential disconnection we talk about, and we spoke about the basic stability. Now, we will also talk about the reactive power consideration. So, when we talk about the reactive power consideration, um, uh, here I would like to discuss uh, that while in the voltage abnormal condition, the DER may be required to inject or absorb reactive power to support the grid voltage, because it is required sometimes that we need the reactive power, or we have to drop it. So the amount of reactive power injected or absorbed, either it is injected or absorbed, will depend on the severity of the voltage abnormality. If the abnormality, whatever the abnormality is, it will be injected or absorbed accordingly. Now, the voltage trip and ride through conditions, voltage trip thresholds we have to talk about. These are specific voltage levels at which the DER control system initiates disconnection. Like there is a threshold from there when it reaches, so the DER control system initiates the disconnection. This starts. The thresholds are set to balance the need for grid support with this need to protect the DER. So the category one um, trip thresholds are generally less stringent, like their threshold are less stringent than those for higher category DERs. So, it's like this, you can say it's an advantage or disadvantage. We'll talk about it. So, category one trip thresholds are generally less stringent. Now, we will move on to the next one, ride-through curves. So the VRT requirements are often defined using ride-through curves. These curves specially specify the duration for which a DER must remain connected at various voltage levels. If you look at this graph, it shows here. I can make it a bigger one, but it's not going to fit in my screen because I have to show you. So if you look at this diagram, you will see what I'm explaining. This is a voltage and a time. Y-axis is the voltage and the x-axis is the time, and it has been shown various thresholds as well. So DER response shell trip to abnormal voltages, it is being shown for DER of abnormal operating performance category 1. In the second table, you can see voltage ride through requirements for DER for abnormal operating performance category. So these are like the two tables we can have a look, and let's move on to the presentation. So the factors that influence conditions, the specific voltage trip and ride through conditions depend on what? Grid interconnections, standards, local utility requirements, the type of characteristics of the DER technology. There are various different characteristics depending upon the DER technologies. And because our topic is IEEE 1547, so IEEE 1547 is a key standard that provides guidelines for DER interconnections. This is where we need this 1547. That includes VRT requirements. The standard has evolved to address the increasing. So I will just move quickly because I have to cover the category 2, 3, and then the frequency and so many things. And because of the time limitation. Now, well, let's talk about the voltage ride through VRT requirements for category 2. So we will talk about additional voltage ride through and difference between 1 and 2. Now, the voltage ride-through requirements for category 2. Category 2 VRT represents an enhanced level of voltage because that was not an enhanced level category 1. So this is an enhanced level of voltage disturbance handling for distributed energy. That may or may not be for the distributed energy, but now this is advanced level where it takes care of the disturbance for distributed energy resources compared to category 1. It signifies that these DRs are designed to withstand more significant and prolonged voltage deviation. Let's say if there is a voltage deviation for few microseconds, milliseconds, so for this category one will work. For the category two, let's say the time period is now a bit more for the prolonged voltage deviations. So the focus is on maintaining grid stability during more severe disturbance. Like if there's a disturbance or the voltage is there for a longer period of time, so we have to have some arrangement for that. So going beyond basic protection. So number one was just for the shorter period of time for the basic protection. So now we have to go beyond the basic protection. So the category two aims to bridge the gap between minimal protection, that is category one, and the robust requirements of traditional power plants. For like if we talk about when I talk about traditional power plants, it means may not be DERs. Excuse me. So this category 2 is somewhere between the category 1 and the robust requirements of the traditional power plants. So additional voltage right through capabilities for category 2 are required to remain connected and operational for longer durations, as I said, and deeper voltage dips than category 1 because, as I said before, the category 1 was for the shallow. This one is for the deeper and deeper dips. So they possess more advanced control systems that enable them to actively support the grid during voltage disturbances. So what happens at this kind of arrangement is like more advanced and more controlled system that enables them to actively support the grid during voltage disturbances. So this includes providing reactive power support to help stabilize voltage levels. As we said before, for category 1, reactive we were talking about reactive power, either injected or absorbed. So here we will talk about that this includes providing reactive power supports to help stabilize voltage levels, so they can ride through more substantial voltage fluctuations without disconnecting, contributing to overall grid resilience. Because it was in category 1, it was just disconnected as soon as some disturbance comes for a smaller period of time. Now, if this fluctuation is there for a longer period of time, it has to keep it working, so they can ride through more substantial voltage fluctuation without disconnected, contributing to overall grid resilience. So our grid should be resilient to this situation. Difference is what is difference of two from one is in two, enhanced robustness. Category two offers significantly greater resilience to voltage disturbances. So in this case, we have the greater resilience to voltage disturbances as compared to category one. Longer ride through times. As I said before, there is a longer lifetime. So category 2 DERs must ride through deeper voltage dips for longer duration. Now, deeper voltage dips for longer duration. Over there, shallow dips for shorter duration of the time. Now, active grid support category uh, in category 2 are expected to actively contribute to voltage regulations through reactive power injection or absorption. So we have an injection absorption here as well. Unlike category 1, which primarily focuses on basic protection, that in case of 1, it is just for the basic protection, but now it is doing the power injection and absorption as well. Stricter requirements, so the voltage trip threshold and ride-through curves for category 2 are more significant. I think it should go for category 2 here. Yeah, graph here. So if you see this, this is just for reference because this is already being given. On the right hand side, on the graph that is on your left side, there is a blue one. DER response shall trip to abnormal voltage for DER of abnormal operating performance category 2 is on the top, and then voltage right through requirements for DER for abnormal operating performance category 2. So these are the two tables. So I'm referring to those and just moving ahead as quicker as I can because I have a shortage of time. Now, the voltage right through requirements. So, if we talk about the voltage right through requirements, uh, what we see is um, that we will define it about category 2, highest level of right through capability. We'll talk about suitable, if it is suitable for high penetration DER system. So let's talk about 3 and move on to the next. Voltage right through requirements category 3, definition of category 3 VRT is number 3 represents the most stringent and advanced level of voltage disturbances handling for distributed energy resources. It signifies that these DRs are designed to withstand the most severe and prolonged voltage deviation. So this is the highest. Two was in the middle and one was very initial. So the focus is on ensuring maximum grid stability and resilience even during major grid events. So if there is a major grid events for a longer period of time with a where most of the equipments are being influenced or being attacked or need some kind of repair or some fluctuation in terms of voltage or frequency, we see this is actually about the voltage. We're not talking about frequency yet. So the focus is on ensuring maximum grid stability and resilience even during major grid events. So category 3 aims to replicate or exceed the performance of traditional large scale power plants in terms of voltage ride through capabilities, because when we talk about traditional large scale power plants, they may or may not be having that. This is what my understanding is. They may not be having a DR. Let's say they're fuel operated or hydro power plants. I may be right or wrong, but this is here we are talking about it. So this is having more capabilities, more performance as compared to traditional large scale power plants in terms of voltage ride through capabilities. Highest level of ride through capabilities category 3 are designed to remain connected and operational during extremely deep voltage dips for extended duration. So it is very important that they should remain connected. They possess high sophisticated control system that enable them to actively and continuously support the grid during voltage disturbances. So this includes providing robust reactive power support to stabilize voltage levels and prevent cascading failures. So in terms of cascading failures, we having a one failure and then the failure is followed by various devices or system, and there is a one fault at some place and it keeps going. So we have to protect this. So this includes providing robust reactive power support to stabilize voltage, and whenever there is a voltage fluctuation, it has to provide some kind of reactive power to the system to prevent the cascading failure, so they can ride through significant voltage fluctuations without disconnecting, contributing to overall grid resilience and reliability as the one before. Suitable for high penetration DR, category 3 is essential for grids with high penetration levels. As more DRs connect to the grid, their collective behavior significantly impacts the grid. So we are just talking, we are not only talking about one or two, let's say there are numbers of DRs connected to the grid, and their collective behavior significantly impacts grid stability. uh, Number three ensures that these DRs can provide the necessary grid support to maintain stability even during major disturbance. So I'm just moving quickly. General notes on voltage ride through scenarios where DRs may cease to energize, impact of net active power export. So we will just talk a little bit about it. Scenarios where DRs may cease to energize. This addresses the condition under which the distributed energy resources are allowed to required to disconnect from the grid during voltage disturbance. What I said before, that it should not be disconnected, but there are some scenarios where DR may cease to energize. So what happens? This includes which kind of situations? Severe and prolonged voltage dips or surges that exceed the DR's ride through capability, because these DRs having there some kind of ride through capabilities. So if it is beyond that, so of course it has to be disconnected. So frequency deviations that are outside the DR's operating range, of course there must be a range. So if it is outside the range, beyond the range, so then it has to be disconnected. Activation of protective functions to prevent damage to EDR or the grid, because we have to take care of everything. So if it is not within the limit of the devices that we have, so it should trip or it should go off. Grid instability that necessitates DER disconnection to prevent cascading failure, because cascading failure we have to be very careful that we are just protecting one or two segments of the entire infrastructure or the grid, and they should not be at the cost of failure to other segments. Impact on of net active power export on VRT behavior. This highlights how the amount of power the DER. Let me just move on to just to show category 3. I'm here. Okay. So impact of net active power export on VRT behavior. This highlights how the amount of power of DER is exporting to this grid affects its ability to ride through voltage disturbances. So, which are the factors? One is the high power export can strain the DR's control system during voltage dips, potentially leading to disconnection. Because if there is a high power export, that can strain the DR's control. Number two is the DR's ability to provide reactive power support during VRT can be influenced by its active power output. So now this is a vice versa. Like we want that reactive power, But the DR's ability to provide the reactive power support during VRT, during that operation, can be influenced by its active power output. So there is like another issue. The degree to which DR must reduce active power output during a voltage disturbance to remain connected. So these are the factors. So many others. So at this point, it's not necessary to go into details because I have to cover the frequency. VRT operational regions. This refers to the defined voltage and time ranges within which DER is expected to maintain connection and support. As I said, the time is important thing and the range is important thing. If it is, it has to remain connected. Let's say, I'll just giving you 3 seconds or 1 minute, or for certain V from V1 to V2. So if it is beyond that limit or it's not within that duration, so it's expected to maintain connection and support only within the limited time and voltage. Specific voltage thresholds and the durations that define the DR's right through capabilities, different operational modes or settings that the DR can employ during VRT. So this is all the details. So let's moving on quickly with low voltage, and we'll talk about low voltage, LVRT, right through, and the high voltage. So the low voltage is mandatory, permissive, and momentary momentary cessation regions. See what are those minimum voltage thresholds and all that. So for LVRT, mandatory, permissive, and momentary cessation regions. So there are four words: mandatory, permissive, and number three is momentary cessation. So what is mandatory region? That defines the range of voltage and time. As I said before, where the distributed energy DRs must remain connected. So let's say between V1 and V2, it should be connected from time T1 to T2. This is the critical zone where the DER is expected to provide maximum support to the grid during the low voltage events. If there is a low voltage event, so the mandatory region is the region where it has to perform the best. Failure to ride through in this region could lead to grid instability. So usually when we design, we define that this is the mandatory region we have to work in this range, in this region, definitely. Now the permissive region, that defines a range where the DERs may remain connected, but disconnection is allowed if necessary. Like this is a second stage. It is less than the mandatory. So permissive is okay, it's better, you should remain. If not, you can disconnect. If disconnection is allowed if necessary, there are conditions. This provides flexibility for the DR's control system to prioritize its own protection or other operational needs. Of course, it needs its own protection as well. The DR's response in the region is often based on its specific capabilities and settings. More details. Momentary cessation region, for the time being, defines a range where the DR is allowed or required to temporarily cease energizing or stop injecting power. I mean, if it is injecting power, there for certain period of time, momentary cessation region is a region where it can stop or cease energizing the injecting power. This is often for very deep voltage dips where continued operation could be determined to the grid on or the DER itself. So this cessation is expected to be brief for shorter period of time, and the DR should resume operation as soon as the voltage recovers. If the voltage recovers, that's fine. So this momentary cessation is over. Minimum voltage threshold, as we have a for maximum voltage threshold, we have a minimum voltage threshold like a limit. These are the lowest voltage levels that DR is expected to withstand within remaining connected and operational. So let's move on quickly to HVRT, high voltage ride through. In this case, what happens? We have to see the response to over voltage events, permissive and momentary cessation operations. So more or less, it's the same or vice versa. High voltage ride through HVRT requirements response to over voltage events. Let me continue the next because I have to go according to see this is what is being defined here. So I'm just defining it in my own words here. So, this addresses how distributed energy resources are expected to behave when the grid experiences voltage above the normal operating range. So, that what does it include? It includes maintaining connection during temporarily over voltage within specific limits. So when there is this over voltage, at least you have to run the system. So it has to be maintained, like maintaining connection during a temporary over voltage, potentially adjusting reactive power outputs to help regulate voltage. So you see the role of the reactive power. Sometimes you inject or is absorb, and it's key is it remains somewhere there. So disconnecting if the over voltage exceeds the DR's right through. This is important because if it exceeds the DR's right through capability, because every DR it has its own right through capabilities. Of if it exceeds, then disconnect or poses a risk to the grid or the DR itself. The ability of the DR to absorb reactive power to help regulate voltage. So I really want to move quickly towards the frequency, and let me move on to this one as well. High voltage almost covered. Now I will be moving on to the frequency, right? So let me check if I'm having the proper recording. Yes. Okay, so now permissive and momentary cessation operator. Permissive operators defines a range of over voltage and time where the DR may remain connected, but disconnection is allowed. So see, in all these situations, sometimes remain connected, disconnection allowed. Disconnect is not allowed. Remain connected. Don't go over. Don't go under threshold. So they are various protocols, various kinds of guidelines and the regions where we see permissive or mandatory or momentary secessions. So if it is one way in LVRT, it's other way HVRT, but almost the mode of operation is same, but the approach is different. So permissive operations that this allows the DR's control system to prioritize its own protection or other operational needs if necessary. Momentary cessation, just like LVRT we discussed, that defines a range of severe over voltage. Over there was for the undervoltage and time where the DR is allowed or required to temporarily cease energizing or stop injecting the power. This is often for very high over voltage where continued operation could be determinant to the grid of the DR itself. Now, let's move quickly to the frequency thing. Frequency right through, we just spoke about voltage. So now, default DR response to frequency disturbances, categories one, two, three, comparison, and then we'll talk about the diagram. Diagram is right here in the presentation. So let's talk quickly. For category 1, 2, and 3 comparisons, this highlights the differences in FRT. Now we are talking about frequency right through capabilities among the various categories of DRs. It includes category 1, category 2, and category 3. For category 1, basic FRT requirements allowing for disconnection during the significant frequency deviations as in voltage. Here is for the significant frequency deviation. Let's move on to number two. Enhanced FRT capabilities requiring DRs to remain connected and support frequency stability for a wider range of deviation. Let's say I'm just giving an example. Let's say deviation is from 10 to 20 hertz. Let's assume this is the middle level. I'm not sure yet, but I'm just giving you an example. If it is within 10 to 20, okay, this is category 2. If the deviation is more, so let's see category 3. Most stringent FRT requirements demanding DRs to provide robust frequency support even during severe grid events. So this differences in the amount of time that a DR in each category must remain online during frequency deviations. Let's say deviation is greater than 30 hertz, 30 to 40 hertz. So number three, let's say if it is 10 to 20, say number two, if it between one and two or four hertz, let's say it's a category one. I'm just giving you a number, I'm not sure. Okay, now um, for general FRT requirements, conditions where frequency right through is not applied. Impact of frequency deviation of on DER. So let's talk about this. There are some conditions where we really don't want those things. So let's see what are those. So conditions where frequency right through is not applied. This addresses situations where the typical frequency right through FRT requirements for distributed energy resource DERs may be waived or not applicable. That includes some scenarios, say, for example, intentional islanding, protection system operation, grid stability issues, specific DR technology, or commissioning or testing. So, whenever this is required, then these are the conditions where frequency right through is not applied. The question is if voltage right through is applied or not. This is a question we have to see. So this addresses situations, right? So which are those situations? Scenarios: intentional islanding. If a DR is intentionally operating in an isolated microgrid grid level, FRT requirements may not apply. Protection systems operation: if the frequency deviation triggers protective relays designs to disconnect. Then the grid stability, specific DER technology commissioning. I'm just moving quickly because running behind the time. Then the low frequency right through and all that. So impact of frequency deviation on DER operation. This focuses on how deviations from nominal grid frequency affect the operation of DERs. This includes what? One is the active power adjustment, number two is the active power adjustment, then operating limits, then the control system response and synchronization issues. So these are some of the factors. The one is the active power adjustment. DERs may be required to increase or decrease active power output to help stabilize frequency. So sometimes there is a requirement to increase or decrease active power output to help stabilize frequency because active power adjustment will can stabilize the frequency. The reactive power adjustment, some DRs may adjust reactive power output to support voltage during frequency events. This is important. Now, the operating limits. Frequency deviations can push DRs towards their operating limits because, as I said, every DR has a voltage limit and the thresholds and the for the frequency as well. So the frequency deviations can push DRs towards their operating limits, potentially leading to derating or disconnection. Because if it will be pushed towards their operating limits, like telling them to go back, potentially leading to derating or disconnection. Control system responses, the DER's control system will respond to frequency changes. If there is a change in the frequency, the control system will respond, adjusting its operation to maintain stability. Then synchronization issues are there. Large frequency deviations can make it difficult for DERs to synchronize, excuse me, with the grid upon reconnection. So almost I'm there. Then there is a diagram. If you look at the uh, I think there is like category one. I was giving you some examples, but here it says zero point 0.5 hertz per second. It's a rate of change of frequency. But yeah, I have to talk about it quickly. Rate of change of frequency, acceptable rate of change of frequency limits for each category. So there is a role of ROCOF in system stability because it frequency is changing, but how quicker it is changing, how slower it is changing, it is very important. So acceptable rate of change of frequency limits for each category. This refers to the maximum rate at which the grid frequency is allowed to change before a distributed energy resource is required to disconnect. So it includes what? Defining specific rate of change of frequency thresholds for each capacity. It means we are talking about the speed of the frequency. Frequency itself has speed of frequency. So defining a speed, specific rate of change of frequency thresholds for each category of DER. For example, category 1, 2, and 3. Category 1 will have the lowest rate of change of frequency limits, meaning they will disconnect at a lower rate of change of frequency. Let's say rate of frequency is zero point 0.5 something, so it will disconnect. Category 3 will have the highest rate of change of frequency limits, meaning they will be able to stay online during a higher rate of change of frequency. So what about number 3? So these limits are designed to prevent DRs from tripping unnecessarily during minor grid disturbances while ensuring disconnection during severe events to protect the system. Now, the acceptable limits are based on grid stability studies and the capabilities of different DR technologies. Of course, different technology has an impact as well. So the role of rate of change of frequency in system stability is that this highlights the importance of ROCOF in maintaining grid stability, especially with increasing penetration of inverter-based DRs. We covered the inverter-based DRs. It was covered by the other group member. So that includes ROCF is an indicator of grid inertia because grid has an inertia, of course, which is the system's ability to resist changes in the frequency. Because if the frequency wants to change from one to another, so there is inertia that will stop it. So rate of change of frequency is also an indicator of grid inertia. High rate of change of frequency values can indicate a rapid loss because if the frequency will change very high, all of the in a speedy way, in a rapid fashion. So there is a chance of loss of generation or load potentially leading to frequency instability. So DRs with rate of change of frequency right through capabilities can help to mitigate the impact of rapid frequency changes by what? By staying connected and providing support. So, in the last two, rate of change of frequency relays can be used. There are relays are there used to disconnect generation or load to prevent damage to the because if it is very quicker, very rapidly, so we have to have the rate of change of frequency relays that can be used to disconnect the generation or the load to prevent damage to the system. Now, the final is rate of change of frequency is a very important part of keeping the grid stable asset. So there is a diagram here, you can have a look. Um, this is like a calculations here. We can talk about it later. Then the frequency and droop capabilities. Quickly, I have to run through this. Explanation of frequency droop control relationship between active power and the frequency. So this refers to a method of controlling the active power output of a distributed energy resource DR in response to changes in the grid frequency. If the frequency is changing, so we talk about the Droop capability. That includes a decentralized control strategy where DRs automatically adjust their power output based on local frequency measurements. So there has to be a decentralized control somewhere else. A proportional relationship between frequency, deviation, and power output change the ability to provide primary frequency response, which helps to stabilize grid frequency during disturbances. So there has to be some kind of ability in the system to provide primary frequency response, which helps to stabilize grid frequency. So this is a decentralized control system. The use of a Droop characteristics, which defines the sensitivity of the DR's power output to the frequency changes. Excuse me. So relationship between active power and the frequencies. This highlights the correlation between the active power output of a DR and the grid frequency. It includes what? As frequency decreases below nominal, the DER increases its active power. So it's other way, like inversely related. As the frequency decreases, like the system goes slow, the frequency goes slow below the nominal, the DER will increase its active power output. It will give more active power. So as frequency increases, of course, the DER decreases active power. So the slope of this relationship is defined by the Droop setting, which must be somewhere here if I can see, or yeah, no, it's not there. Anyways, so as we can, the slope of this relationship is defined by the Droop setting. The relationship is typically linear within a specified frequency range. What about if it is not within the specified frequency range? It may not be linear, I assume. So this relationship is fundamental to how DRs contribute to frequency regulation. So now we have covered high voltage, low voltage right through category 1, 2, and 3. We have covered the frequencies right through which we talk about the rate of change of frequency and we spoke about the this Droop capability. So I think this is almost on. Then interoperability of the DRs, communication standards, and IEC 61850. This will be covered by um, my friend Mohammed. So thanks. Any questions you can ask? We actually don't have a lot of knowledge so far, but this is like a general view, or just like a visionary look, and prepared the preparation, the presentation. And there are so many questions. Maybe may ask the instructor. The instructor can ask us so many things. We can just discuss. It's not the final. We still be working on it. Thanks everybody for being with me. Thank you.